did it 6 times, and we had exits, right? The black was after the first three trials, and then the red was after the next 3 trials. After the, you could just tell by looking at the black, right, that 0.5 was obviously the highest, right? But 0.4 and 0.6 weren't that far behind, right? And then 0.3, and then it was symmetric, but it kind of wasn't a clear leader, right? And then what happened after we did the second 3 trials? So after we did the 6, what happened? What became more clear on the visual here? 0.5 was pulling away, right? 0.5 was pulling away. And that makes sense because it's the true probability, right? If I have 52 cards, playing cards, half of them are going to be red, half of them are going to be black. We know that. We know if I had all of the playing cards ever created and I were to put all the reds in one pile and all the blacks in another pile, it would be 50-50 exactly. We know that, right? But this is just showing that. And if we were to do it today, we were to do 6 more, 0.5 would pull away farther and farther and farther. So what we're starting to see is the true answer, the true proportion, right? Each of these are p hats because it's a sample, right? But the true proportion, the real answer, is p. That's what we're looking for, right? I don't have all of the cards here. I don't have all of the playing cards that ever existed at my disposal. I just have the cards I gave you guys yesterday, right? That's all I have. So what I'm doing is I'm using samples to kind of see what the true parameter is, right? It's a lot easier to take samples than to collect the population cards that ever lived, that ever were created, okay? So by doing that, it's called a sampling distribution, right? If I had you guys do it an infinite number of times, 0.5 would be by far the highest bar because that's the true answer, okay? That's what a sampling distribution is, okay? We did a bunch of samples, we put them up there, we take a look at what's going on. That's exactly what a sampling distribution is, okay? A true sampling distribution would do it an infinite number of times. We would just keep doing it and not stop. But we can't do that, right? So we just did it. We just did 6 trials on there, okay? Okay, so sampling distribution, kind of talked about that. In the previous activity, we took a handful of different samples of 10 cards, right? You guys flipped over 10 cards. There are many, many possible SRSs. You guys did a whole bunch of SRSs. You shuffled them up, right? And then you flipped them over. The simple random sample. You guys did 6 of those, right? Each sample size was 10 from a population size of 52. In fact, there are 270,725 possible SRSs, different things that could have happened. There are 270,725 different things that could have happened when you flipped over the cards. Lots of different outcomes that could have happened. Okay, if we took every one of those possible samples, calculated the sample proportion for each, and graphed all of those, we'd have a sampling distribution. Okay, so sampling distribution of a statistic is the distribution of values taken by the statistics in all possible samples of the same sample size from the same population. In practice, it is difficult to take all possible samples of n to obtain the actual sample distribution of a statistic. Instead, we use simulation. So sometimes they'll simulate this. You can simulate it as well. We won't do that in class, but you can do that too. Okay, so here we go. How do I describe? We talked about that, right? How do I describe the sampling distribution? Well, there's 3 things you need to describe. Center, spread, center, spread, and shape. The center, and spread, and shape. Those are the 3 things you need to describe. They'll ask you to describe about the sampling distribution. Okay, so how do you do that? Right here. Okay, so the fact that statistics from random samples have definite sampling distributions allow us to answer the following question. How trustworthy is the statistic as an estimator of the parameter? So how trustworthy are all of those x's in actually predicting what percent of red there are? Okay, so we have center, spread, and shape. Okay, a statistic is called unbiased estimator of a parameter if the mean of its sampling distribution is equal to the parameter being estimated. What does that mean? This is what that means. I'll show you right now. If I were to take all of those x's represent a decimal, right? If I was to add up all of those, so 0.2, like if I was to have all of you guys put this in L1, 0.2 plus 0.3 plus 0.3, 0.3, 0.3, 0.3, 0.3, 0.3, so on and so forth for all of them. Did one var stats, found the average. What do you think that average would be close to? 0.5, right? We can see that. It's 0.5, right? Well, what it's saying is if we did this an infinite number of times, and I were to do that, calculate the average, it would be 0.5. Because isn't that the true answer there? The true proportion? That's what that's saying. It's unbiased if those equal each other. Okay?
Is there a way to calculate the true thingy, or is it going to be a given?
Most of the time, to find the true parameter, it's not going to be possible. So what we're going to do is we're going to use the sample mean, or the sample average. That's what we will use, yeah. Because most of the time, finding the true population proportion or the true population mean will be impossible. For ours, it wasn't impossible because we know that half of all cards that are made are red and half of that are all cards are black, right? We know that, right? For a lot of the problems we do, we won't know what the true is. So we will have to use our the samples for that. And that's what we're going to do. That's the second part of this chapter. Okay, we will do all those. So the mean, the center of a sampling distribution will always equal the mean of the population for any sample size. So like for the card, the mean, the center of that distribution is 0.5. P equals 0.5. Okay. The spread of a sampling distribution is affected by the sample size. So if the sample size goes up, the spread will go down. If the sample size is low, the spread will increase. So our sample was 10, right? We did 10, right? That's pretty small. So I would expect a spread or variability, standard deviation, to be very big. But as we get a bigger sample size, that number goes down. Okay? So one of the popular questions you see on the test for this chapter is, how do I get spread and variability to go down? Because variability, if you want to be true, if you want to be accurate, you want to have low variability, right? Makes sense. You want to have low variability if you want to be accurate, right? Well, how do I reduce variability? How do I get variability to go down? There you go. It's affected by sample size. That's the only way. Increase the sample size. So if I want to reduce variability on this one that I just did up here, instead of flipping over 10 cards, I would say let's flip over 20 cards this time. Let's do 20 cards. Shuffle, flip over 20 cards. Figure out the percent of red. What would happen here is you would see a lot less variability. You would see a lot less variability. We wouldn't, so like right now, it's kind of like that, right? Still symmetrical, right? If we were to do 20 cards instead, what would happen was it would get a lot less variable, right? So some of these guys over here wouldn't exist. because if I have a sample size of 20, they would have a slower chance of happening. Let's say we did 30. Do 30 cards instead and find the percentage. That would get even tighter. And then even thinner and thinner. Less variability. As sample size goes up, variability always goes down. Okay? Specifically, larger sample size result in smaller spread or variability. Okay? So here's some kind of visuals for you. N is sample size, right? N is sample size. So if I took a sample of 100, look at that picture there. If I took a sample size of 25, look at that picture there. What do you notice about the two graphs? What do you notice about them? What's the difference between them? Do they have different shapes?
Yes.
What would you consider the top? What would be, what would, like if you had to give this shape a name? Symmetric, right? Symmetric. Kind of normal distribution kind of looking, right?
Oh, yeah.
What would this one be? Symmetric still, right? They're both normal. The difference is what?
There's more data in the middle.
Exactly, right? The data kind of is squished in, right? Means there's less variability. There's less, right? There could be some X's here, right? Some X's in here. Over here, there's no chance of it. All of the data is closely packed in, right? Less variability. Why does this one have less variability? Because it has a bigger sample size. Okay, the bigger the sample size, the less the variability. So as n increases, variability goes down. Okay. But you notice the center's still the same, right? Center's right there, center's right there. Whatever number it is, I don't know what number it is, what value it is. So just like that. This is based off samples of 10, right? 10 cards. If we did 20 cards, 25 cards, 30 cards, 35 cards, right? It would start to get less variable. Okay. Okay. And then what would happen if we did, what would happen if I had a sample size of 52 cards? Yeah, there would be nothing else, right? There would just be one long line of X's on 0.5. There would be nothing else because we know that 52 is the whole population you have, right? There is no sample. Okay. So that's what it would eventually get. It would eventually get to, so that only these would exist. Okay. Okay, so biased versus unbiased estimators. So if it is biased, population parameter means the true answer, the correct answer, 50% for the cards, right? What do you notice about the graph and where the arrow is at? For the first one, for this top guy right here.
The graph meets the arrow.
They're in the same spot, right? The graph, the average of the graph is right here. And that's also the correct answer, right? That's what we wanted. That's what we did. We did that, right? That's called an unbiased estimator. Unbiased. That's what we want. Unbiased means I have no say in it. I have no say in how the sample was done or the cards that got chosen, right? Down here. Yeah, what was way off? What is, you're right, way off. What is way off?
The data or the graph.
The graph, yeah. So according to the graph, this should be the true answer over here.
Yeah, that's not.
It's not even close, right? The true answer is over here. So that's like us saying, that's like the highest bar being somewhere over here, being 0.8. Imagine if 0.8 was the highest, right? Something went wrong. Something went wrong somewhere. We didn't shuffle the cards correctly. We didn't follow the directions correctly. Something happened, right? That would be called a biased estimator. Okay? So that's what we want. We want we want two things. We want the true answer to show. We definitely want that. We want the true answer to show. But we also want that to actually be the true answer, right? Those are the two things that we want. We want to have one stand out. It did. 0.5 stood out, right? 0.5 stood out. But we want that to also be the actual answer. We don't want that to be not the right answer, right? So if those two are equal, we did it correctly. It's called an unbiased estimator. Okay, unbiased estimator. We want something to stand out, and we want that to actually be the true answer. Okay, makes sense? Okay. Right. Sometimes people use it as a dartboard, right? This one is I'm throwing darts at a dartboard, and they're all pretty close to each other. All the darts are pretty close to each other when I throw them, and they're all around the where do you want to hit on a dartboard? Bullseye. They're all around the bullseye. That's what I want, right? I want them all around the center, in the center, right? All together in the center. This one is they're all together, but they're somewhere on the outside, right? So I was accurate. I'm like, I'm accurate. Exactly. Who cares, right? You're not even close to the center, right?
You're hitting the board, but like, I don't know, you're hitting on the side.
Exactly. Right? You're accurate, but no one cares because you're not scoring points. Yeah. Okay. That's not what we want, right? Exactly. Exactly. So we want both. I want to be able to be accurate, but I also want to score points, right? That's this one up here. This one is I'm accurate, but it's nowhere near where it needs to be. Okay. Okay. So bias has to do with center. Okay. So that's where we want. We want the center of our sampling distribution to match what actually is the true answer. All right, last slide. Okay, so let's look at the top.
Yes, my favorite distribution. A line.
That's a line, right? If it's a line, it's a uniform. Why is it called uniform distribution?
It's all the same.
Exactly. It's all the same. It's all the same, right? If you're in a uniform, everyone looks the same. So they should have drawn it like this. It's supposed to be like, okay, the bounds there. But that's uniform. Okay, so picture that I have a population that all looks the same. That means there's the same chance. For example, 20% of the students in the class get an A, 20% get a B, 20% get a C, 20% get a D, 20% get an F, right? That's what uniform distribution looks like. Everything's the same percent, right? Uniform distribution is kind of like rolling a die, right? It's all the same percent chances of getting a 1, getting a 2, getting a 3, so on and so forth. So let's say I have that, something that looks like that. After I take two samples, a sample of 2, then it starts to become less uniform. Not uniform anymore, right? What happens when I take a sample of 30 from that population? Right? Variability's gone away. Variability's gone away. Okay. The next one, let's say skewed. Skewed, which way is skewed? Skewed right or skewed left? Skewed right. Yep. Skewed right. Skewed to the right. Yeah. So probably told you guys this, but if you were on top of the mountain, which way would you ski? To the right or to the left? If you ski to the left, you're probably dead. If you ski to the right, you have a chance, right? If you ski to the left, you got no shot, unless you're a world pro skater or a skier. Exactly. Okay, not a good look. Okay, so anyway, Population. So what would be skewed to the right? A test that is what? Hard. Yeah, very hard test. Very hard test would be skewed to the right. Okay, so let's say my population is everyone who took this test scores from a test that was really hard. So let's say I had 100 students. That's the population. I graphed. And this is what it looks like. Okay, so let's say I took a sample of 2. What is happening to the picture? Less skewed, a little less skewed, right? Now what happens when I take 30, around 30, and I graph those 30? Variability goes away, right? Variability goes away, and the true answer is kind of showing itself, right? This is the mean, right, in the center. The center is the mean. Okay. Normal distribution, just like we like. We like pretty nice normal distribution. It's nice and symmetrical. That's what we like, right? Unfortunately, not a lot of things in life are perfectly normal. There are some things that are normal. People's heights, people's weights, people's IQs. If you were to have every single person in the world or in the United States or in the world and measure their height, graphed it, guess what? It'd be normal. It'd be normal. No, weird how that works. So weird how nature works, but that's how it works. Same thing, not even humans, animals. Size, tall, height of any animal or length of whatever animal. Okay. So if I took a sample from this of 2, obviously it's still normal, right? It's still symmetrical, but what's the difference between them? What has gone down? Variability, yeah. The range is still out there, right? The range is still, but variability has definitely gone down. And then if I take a 30-ish, that's what we want, right? They all look around the same. That's the key right there. It doesn't matter where you started. What matters is your sample size. What sample size is perfect on this thing? The whole, yeah, the whole. Obviously, if I could do the whole, perfect. But if I couldn't do the whole, what sample size would be ideal? 30-ish, 30-ish or more, 30-ish or more. Because it doesn't matter what it looked like at the beginning. If you take a sample of 30-ish and do it correctly and graph it, 2 things are going to happen. One thing, it's going to be normal distribution. That's the first thing. The second thing is variability is going to be really low. Variability is going to be really low. And the center will match. You see, like the center here is right about there. The center here. The center here. Okay. Alrighty. Let's see. So we haven't done a lot of calculations. I don't think we've done any calculations this in part 1. This is 7.1. This is the assignment that I assign you guys tonight will be from 7.1. There's not a lot of calculations. Sometimes that's good. Sometimes that's not so good because things that don't have calculations mean it's conceptual, right? That's where 7.1 is where your multiple choice questions are going to come from. Okay. 7.2 and 7.3, which will start tomorrow, there's calculations. There's quite a bit of calculations. That's where your free response questions are going to come from. Okay. So that's how I divide it. So their homework tonight, it's not going to be a lot of questions. It's not going to be a lot of calculations. There's going to be no calculations. It's just going to be kind of conceptual based off that. Yeah. Okay. Was that? It's still theory. Yeah. It's all concept theory. It's all that stuff. Yeah. Theoretical stuff. That's prime multiple choice stuff. Multiple choice question stuff. Today's Tuesday, Thursday. It'll be due Thursday. Okay.